What we did? What did we do? On Sunday, we discussed. Wait, no, battery. It's fine. No, we discussed the concept of Taylor series. I want to remind you the important things we've already said, the main things we've already said. Why aren't you charging? Thank you. We discussed um, Taylor series. If a function f equals power series an x minus a, then the an must be the following. It is the nth derivative of f at a above n factorial and multiply by x minus a. It starts from 0 and never ends. For example, for that, when this is Taylor series, when a is 0, we call it the Maclaurin series or expansion or whatever. Now the big M, for example, we are already familiar with the geometric series, and on Sunday we have seen the Taylor series of e to the power of x and of sinus and cosinus and other very nice examples. For example, let's write down e is the sum of x to the power of n above n squared, n factorial. Okay, what we started to discuss the using of Taylor polynomial as an approximation for the function itself. We can write the function f, which is the sum of f and a above n factorial, as the sum from 0 to some big N, and the sum from big N plus 1 to infinity. We call the first one the Taylor polynomial of order n around a of f, etc., etc. And the second one we are already familiar with. It is the remainder Rn. So we can say that the Taylor polynomial Pnx is an approximation to the of the function f fx is prox Pnx. We want to thought about it after the last lecture Sunday. I think the appropriate word should be estimation. To estimate the, or I don't know, right? When I say it out loud, I don't think it's true. Right. Yeah, but we've already used the word approximation for P and for F. What we want to talk about is the Rn. Want to find an upper bound to Rnx to estimate? No, approximate. Oh, estimate. להעריך, again, in Hebrew. The error, and the error is the absolute value of the remainder Rnx. Want to find a good, yeah, upper bound, not complexity curse, not whatever you do in computer science. We don't have to prove that it is tight or something like that, but we will show how to do it, and this is what I expect you to do when you encounter such questions. Rnx, the remainder, is a series. So we need to find a nice way to express it, write it down without an infinite sigma, or at least an easy way to find an upper bound, a good upper bound. And as I've already told you, that's how we finished the last lecture. We first of all, we look at alternating series. There it's pretty easy to find an upper bound. And then we will discuss the general case. So alternating series. Let's be clear. An alternating series is a series that is minus plus or vice versa. First of all, or firstly, discuss alternating series. Series of the form -1 and Vn, where Vn is going to 0, decreasing series. We know by Dirichlet/Leibniz from Infi1 that such series do converge. If it is divergent, we don't have to talk about it at all. But what I want to show you here today is that, and maybe when I teach Infi1, at least in the last years, I talk about it. Don't know if Eris did it, so I want to do it from the beginning, but let's do it in the shortest way possible. First of all, I claimed the following claim. When it comes to alternating series, the error is bounded by the element by her first element, by its by its first element, meaning that Rn is bounded by Bn plus 1 without the -1, of course. For example, let's use a different color. It goes to 0. If it decreases to 0, it must be positive. Yeah. Preferred color? Red. It's too shiny, too bright on the white background of the PDF. Let's go with olive, orange. For example, the classic case of an alternating series is the sum of -1. Yeah. We want to start with plus another minus. You can start with -1 plus n plus 1 or something like that. It is -1 plus half, -third plus quarter, and so on. Now, let's, for example, take a look at the first three elements. They are an approximation for the all sum. And this is by our notation P3. Can you see? So it's too bright. Okay, P3. And the rest of the sigma is what we call the, no, the remainder, it's R3. Now, as you can see, we don't know what exactly R3 is, but we can easily say that it is smaller than quarter, because it is quarter minus 1 over 5. And then you add something with something smaller because the sequence is decreasing. So you end up with something smaller than quarter, which is the element, which is the first element of the remainder. Now it works not only for 1 above n, it works for every decreasing series sequence decreasing to every sequence decreasing to 0, multiplied by minus 1 to n, becoming an alternating series. I'm not going to automatically write it down, and it's already enough with our example. So when we need, no, we don't want to do that. So when it comes to alternate series, we can use this inequality in order to find our upper bound, an upper bound. And I'll show you two examples. For example, I want to do two examples. Each way of the question, I'll show you right away what I talk about. First of all, we approximate 1 above E, okay, for example, using the Maclaurin polynomial of order, I don't know, number you like, 3, of a to the power of x, and then we estimate, this is the right word, the error. Show you how we do it. So, the Maclaurin polynomial of order n of 3 of fx, who is it? Yes, what you mentioned here, but we are finishing with 3, not with infinity. So it's just an approximation, we already know. If we write it explicitly without the sigma, it is 1 plus x of 2 plus x squared of 2, of course. And it is x cubed over 3 factorial, which is 6. Now, we need 1 above e. So which x should we put in here? Minus 1, of course. 4 and 1 above e. Put x is minus 1. So e minus 1 is approximately 1 minus 1 plus and 1 above 2 minus 1 above 6, which is the third. estimating the error, we're using what we talked about it here, right? Um, Now we know that e to the power of minus 1 is the sum from 0 to infinity of minus 1 to the power of n, which is this sum plus 1 above 24 minus 1 above 120 plus 1 above 720 and so on. Now the remainder is specifically here n is 3 and we have x is minus 1, so it's R3 of minus 1. And it is the sum beginning with 1 above 24, which is, and it is bounded by its first element. So one can say what is our estimation of the error? It is smaller than 1 above 24. And it is enough. It's not the exact, the real error. But when you are facing an alternating series, as the lecturer is the one who decides, it is enough to use the element you start with as the upper bound. It is fine. Well, now what I want to show you is that if we, let's go all together to the browser and Wolfram, I use Wolfram for example, for simple examples. We can calculate the real error. I mean, on one hand, we have 1 above 8, the real value, and on the other hand, 1 above 3, the estimated value, and we can see the error. It is approximately 0, 0, 3, 4, 5, blah, blah, blah. Why do I call it the real error and not just the real error without choreography? Because, as we already mentioned, it is not the number itself. I mean, you know what? Wolfram calculated for me. Let's see. And then I can ask him more digits, more digits, more digits, more digits with the whip. Yeah. Now that's what Bnei Israel did in Egypt. Calculate digits for Pharaoh. Look at that. Look at that. How many? No, you're not allowing me anymore to look at the fewer digits. But still, it's nothing compared to the real number. The real number has an infinite number of digits after the dot. As we already saw, you take all the servers. Let's say that Trump goes and he impeaches every president in every country and forces every country to use every computer and every cell phone and every smart refrigerator. Calculate the digits of 1 above e minus 1 above 3. We will not finish the test. Never. So what Wolfram does, it's not the real value, it's approximations. Just a pretty damn good approximation according to what we can do by our hands. And what I want to say is that we got our upper bound, 1 above 24. We can use our calculator to calculate the real error. Here it is 1, 0, and 0, 3, 4, 5, 4, 6, 1, blah, 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 blah. And on the other hand, we can talk about 1 above 24, and we can see that, yes, it is 0, 4, 1, which is greater than our real error. So yes, the first element does bound error, you should do, it's not good for any, but you should do it for yourself, check it in the calculator in order to see that you didn't miss the index, perhaps take one element further, which can be already smaller than the real error. We need to, we say check ourselves before we reconcile. Yeah. Okay. Any questions about the part with the real error or what didn't hear the word from? Any question about how we estimated our error by method? Okay. So now I want to ask you a question from a different point of view. If you think about it, what happened most of the time in reality, we are not giving the order of the polynomial, and we need to find the upper bound. It's usually the other way around. We are given an upper bound. You know what? We are going to build a bridge. We're going to paint a soccer field. We're going to operate some complicated brain. How do we call the brain surgeon? What does it do to the brain? It's not surgery, right? Surgery. A surgery, right? A brain surgery. Thank you. We need to know maximum 1 millimeter error where we put our little scalpel. And we are giving the upper bound of the error. It's our job to find the n that will lead us eventually to an approximation with such an error. I mean, look at the, for example, for that, different point of view. Different point of view. We want to calculate 1 above E with I call it in Hebrew diuk, accuracy. But you don't have to use this word. With what? No, don't have to write that way. Of 1, 1, 1, 0, meaning that I want the error to be smaller than that. How many elements of the Maclaurin polynomial or series, because we're looking at the math of all the sum. Series are needed in order to achieve such accuracy. We need the question is the other way around. Okay, we are looking for the n. We are looking for the minimal n such that
Yes.
the minimal n such that the error yet again at -1 is smaller than 1 above 1,000. Now look for my how did I put it in words? Look for the minimal n.
Yeah.
Let's say that 5 elements are enough. And we calculated 7 elements. We did better than expected. We're having more elements than we need. So mathematically speaking, it is not so bad. By the reality point of view, let's say we want to calculate with accuracy less than accuracy of 1.110, and we say, you know what? Let's calculate million elements. Well, million elements will probably do the job, but calculating million elements, even asking the computer to do so, will take some time. Take electricity and other resources we don't want to waste. So it is, by the reality point of view, it is important to find the minimal n. Instead of 5, you've written 6, it's not bad at all, yeah? But instead of 5, you write 5,000, it's problematic. So how do we find this n? We're not looking for, yeah?
Yeah, I just reminded of the quote of anyone can build a bridge, only an engineer can build a bridge. That's very well done.
Yeah. Stretch the range enough.
Yeah, so we know that the remainder is less than the last element or the first element after can do that. My question is like when you have a factorial and whatever, how do you make the equation not exact?
Okay, so first of all, it is enough, yes, because it is an alternating series. We know that the error is bounded by the element it starts with, which is 1 above or 1 above n plus 1 factorial in our specific case. So it is enough to find the minimal n that satisfies 1 above n plus 1 factorial is smaller than 0.001. Now, two things about it. First of all, as I've already said, it is not the tightest upper bound, okay? We are looking at something greater probably than the remainder itself. And of course, we don't usually have a specific n that gives us the exact number we want as an upper bound. So it's two inequalities that we are enlarging the real error, but it's fine. That's why I call it an estimation, and it is good enough to work with. But one can say it is enough to find the minimal, but it is sometimes not necessary. I mean, maybe this inequality holds from n equals 5 and so on, but the remainder itself, the real error, which is smaller than 1 above n plus 1 factorial here, is maybe smaller than 0.001, starting with n equals 4 and not just n equals 5. Maybe. I do not care. And I do not mind. That's how we do it. By our syllabus, by the time we have left, which is not a big amount of time, and so on. Now, for your question, in the bottom line, we have an inequality we need to solve. But it's not actually need to solve. We just need to find the n that satisfies it. And first of all, what dimension we don't want to calculate 5,000 million elements. And secondly, proof by common sense. We have a 3 hours exam. We have a lot of funny syllabus. We cannot waste all 3 hours on calculated elements. So probably a small, relatively small n. How do I solve this? In the bottom line, how do I solve such inequalities? I just plug in n equals 1, 2, 3. until I find the correct one. Now, it's not that terrible. We don't have to start from zero. We can see that for n equals 5, we get 6 factorial, which is still 720, which is smaller than 1,000. So the fraction is actually bigger than our desired accuracy. So how do we find this n? How? Trying. Prove by trying. Yeah, by sheer real. By trying. Here n equals 6 is the first to satisfy our inequality. And so our desired approximation is the sum from 0 to 6, which is that. And just look for the phrasing of the question. How many elements of the Maclaurin series are needed? So n equals 6, but because we start with 0, there are actually 7 elements. Now, someone wrote down 8 elements. It is not a big mistake. If you wrote down only 6 elements, well, maybe here the error is still not smaller than 0.001, so it is a mistake. Um, let's go together to, where is it? The Wolfram again. On one hand, we have 1 above E. On the second hand, we have our approximation, 1 minus 1, plus 1 above 2, minus 1 above 6, plus 1 above 24, minus 1 above blah, 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 blah. And what do we have here? As you can see, it is indeed smaller than 110. It's actually a tenth of it. If we give up on the last element, it's bigger. So we had here, the last element is necessary, but then again, it can be that even without him, we are still good because we don't look at the real error. We look at bigger. It's the bigger thing. It's first element, and then we look for the minimal n that satisfies it. But you know, here and now, go back to the leaks. Here, the first n that satisfies our inequality, which is 6, it gives us 1 above 7 factorial, which is more than 5,000. So it's 5 times smaller than the desired estimation. And yet again, it is fine. That's how we do it. That's how we roll. Okay. What we talked about here is about an alternating series. The next question is, what do we do in the general case? Every series? Of course, what I will say now can be used for alternating series as well, but I'm allowing you to use the first element of the error as its upper bound when it comes to alternating series. So you should use it because it's easier than in the general case we are going to see right now. Before that, any questions about what we've already told here? Okay. General case, but I write it down is that way. The Lagrange, that's I write down his name, I think. Lagrange form of the remainder Generally speaking, okay, not just about alternating series. Um, we've already said our problem is with estimating the error that the remainder, the error is the absolute value of the remainder, that the remainder is a series in an infinite sum. We need to find a nice, without summation, form of the remainder, or a nice with a form without summation of an upper bound of it. So when the series is alternating, a nice upper bound is the element the arrow starts with. Perfectly fine. What can we say about the general case? This is what Lagrange says. There are different ways to different nice expressions for the remainder. Some of them, looking at it is from different points of view. For example, there is the piano. It's already not piano, the piano. It's with E. This is the dude, of course, which he looked at the remainder from the asymptotic point of view. I mean, it is going to zero when x goes to a, but how quickly, how fast, or of what it is. It's not in our syllabus today, which is maybe for the next years I should put it in because it's more computer sciencey, but not today. I want to say to the god of piano, not today. The Lagrange form of the remainder is pretty ugly on the first look, pretty decent on the second look, but I want to, let's make it clear. In calculus, we have a bunch of theorems that says, you know what, there is a point such that, without saying who that point is. I mean, we know the intermediate value theorem, f is positive here, it is negative there, so in between, it goes to 0. In which point? And the Lagrange mean value theorem, and Cauchy mean value theorem, and Weierstrass theorem, you know, a function is continuous in a closed interval, there is a point which is the maximum. Fine. Which point? We don't know. The Lagrange form of the remainder is the same. It says that there is a point in which the remainder is blah, 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 without saying what the point is.
How does it deal with how does it deal with diverging images? Or does it not?
No, because we know the series converges to f. Um, so we use the Lagrange form, when we want to estimate error and the series is not necessarily is not alternating. Okay. When it is alternating, we use the first element of the arrow, as we already mentioned and showed. So Lagrange says the follows. We are not going to prove this theorem. In previous semesters, not in semester B, was the missiles from Iran and so on, but on semester A and before that, I sometimes managed to prove it. We had enough time, but here we want to have full 6 lectures. That's what we have. Probably I should have had 7, but whatever. About the multivariable calculus, so we leave the proof for the previous semesters. Just say the theorem itself. Lagrange says that if f is differentiable n plus 1 times, I mean, it doesn't necessarily have to be a series. I know that we have the polynomial, and the rest of it, the difference between the function and the polynomial, that's what we call the remainder, even if the remainder is not the rest of the series, because we don't have it, function not differentiable. N plus times at some point A, Then then for every x in which the series converges, then for every x, there is a point C, or there is a C without the word point. There is a C between A and X such that the remainder, let's write it down with big N, what we did. The remainder is the n plus 1th derivative at C above n plus 1 factorial multiplied by x minus a to the power of n plus 1. It is very similar to the n plus 1 element of the Taylor series. The only difference is at which point we find the derivative. Just a, right?
For McLaren, then it's only at the X, or does it not exist?
For McLaren, a is 0. That's it. That's the only difference.
Okay.
Yes, yes. C is between a point we don't know which point, but there is a point such that C is between A and X. And now we use, and the only difference is the C instead of A in the derivative. Now, can use this formula to estimate an error when the series is not alternating. What do we actually get is some expression of C, and we know the range of C between A and X, so we can approximate it and find an upper bound to it. Let's go through an example. Let's approximate. We approximate, let's say, the square root of 2 using or with the Taylor. That was with big T, right? I sometimes miss it. With the Taylor polynomial of order. Which order? 5. Okay. Of order 5 of the function square root of x around a equals 1. And then we estimate the error. Okay. Let's do it. Let's ball. Here we are not familiar with the Taylor series of square root of x, and moreover, it is not so easily achieved from one of our 3 starters. Not E, not sinus, not the geometric one. So we need to calculate derivatives and the Taylor polynomial by hand. It's not so terrible. I mean, if we finish it, we can know that we can find the Taylor series of it if needs be. I use square root of x around 1. It can be square root of x plus 1 around 0 if you prefer 0, but of course we do what we are given to do. So by definition, the square root of x equals the polynomial you asked for order 5, which is the sum from 0 to 5 of fn at 1 above n factorial x minus 1 to the power of n. we need to calculate the square root to approximate the square root of 2. So we will put x equals 2, which leads to the following term. So easy peasy, lemon squeezy. We need to calculate all these derivatives and just put them there in our formula. You know what? Let's write down a little more explicitly. The square root of 2 is approximately the value at 1. That's what you get when you put n equals 0. The 0 derivative is the function itself. And then the derivative at 1, and then the second derivative at 1 above 2, and the third derivative at 1 above 6, and the fourth derivative at 1 above 24, and the fifth derivative, it's enough tags, right? At 1 above 120. Now let's find the derivatives. We know them. F1, the function is square root of x, right? So F1 is just 1. That's how I want to do it. Let's write it down in a matrix, so which will wait less space. No, not that. One column. Okay, so F1 is just 1, square root of 1, which is 1. Okay. Now, the first derivative, as I already told you before, likewise when it comes to multiplying matrices, finding differentiate differentiate roots. I'm an adult, okay. I have PhD in mathematics. I'm a father of more than one child, etc., etc. When it comes to finding derivatives of square roots and roots generally, I write it down as with using the formal way. It's x to the power of half. Then when I differentiate it, the half jumps out, as we say in Hebrew, gives us x to minus half. And when we put 1, it is half. And let's get down. No. Write it down. The second derivative, the minus half jumps out, is minus 1 above 4. X to the power of minus 3 above 2, which leads to f2 tags at 1 being 1 above 4 with minus. And f3 tags, the minus 3 above 2 is jumping out, leading to 3 above 8, x to the power of minus 5 above 2. So the third derivative at 1 is 3 above 8. Now what about the fourth derivative? Minus 5 above 2 is jumping out. We are left with, you know what, let's write down like that way, minus 3 multiplied by 5, and it is 16 here. X to the power of minus 7. And R finishing with minus 15 above 16. And finally, the fifth derivative, the minus 17 goes out, it is a positive coefficient again. 3 multiplied by 5 multiplied by 7 above 32. X to the power of minus 9 above 2. So the fifth derivative at 1 is 105 above, yeah, 32.
Maybe I can come up with more. Why do we set 8 to 1?
Why do we say what?
8 b1, right?
That is what we are asked to find it using the polynomial with a equals 1. See, specifically, if the function is square root of x, we cannot use a as 0 because the function is not differentiable there. It's on the edge of its domain. Um, so, can say what is our approximation. Square root of 2 is 1 plus half plus minus 4 minus square root above 2 and 3 above 8 above 6 and minus 15 above 16 above 4 and 105 above 32 above 120. Let's calculate each one of these. You know what? No, I did not do it in the lecture of the Hebrew speaker. So I use the Wolfram just for a second. Don't have to go there with me. 1 with 1 above 2 minus 1 above 8 plus it is 3 above 48 minus 15 above 16 multiplied by 24, whatever that be. And the third last element is 105 above 32 multiplied by 120. It is it is actually a nice number. It has a finite decimal form. It is 1, 4, 2, 5, 7, 8, 1, 2, 5. Okay. Now for estimation.
Can I ask a question?
What the question is?
Oh, why are we taking it specifically around a equals 1? Does it matter? Does it change
Yeah,
the
that's
approximation?
what Thomas asked. It's what we're given in the question. I could have asked you to use the polynomial around a equals 3 or using the function of square root x plus 1 around a equals 0, something like that. We are
Okay.
given the a we're working with.
All right. What about if we aren't given it? Like theoretically, does it matter which a we choose?
I mean, in reality, when we have the freedom to choose which function around which a we are calculating the Taylor slash Maclaurin polynomial, one can ask, easier to approximate square root of 2 with the Taylor polynomial of square root of x around 1, or it is easier with the polynomial around a equals 3 or maybe the function is square root of x plus 1 around a equals 0. Well, in order to get the same accuracy, which polynomial requires the least number, the minimal number of elements? It is a legit question, but what are we focusing here today and in our course in general? Is the mathematical point of view that the reality point of view. So we are given the function and the order and the point A. We are given the value we need to approximate, and we use them to approximate the value.
Okay. Will the approximation be the same if we use a different A, or will it be slightly different?
Probably not. I mean, for the
But
same number of elements, we may get a better or a worse approximation. It depends.
cool.
Any other questions? So now for estimation, now by Lagrange, we know that there is a point C between X and A, such that, copy and paste. Okay, so totally fine. But here in our example, we know that n is 5 and x is 2, what we put in the function, and a is 1. So we are looking at the R6 of 2, R5. That's the sixth derivative above 6 factorial, and it is 2 minus 1 to the power of 6. Write it down as 5 plus 1. Okay. 5 plus 1. 2 minus 1 to the power of 5 plus 1, which is the sixth derivative of the function above 720, yeah. And we know how to calculate the sixth derivative here. Derivative is this one, but the minus 9 above 2 is jumping out again. We have 64, and we have C minus 11 above 2. Which leads to the error, the absolute value of the remainder, not R2, it's R52, is the absolute value of this, which is the absolute value of that. No, yeah. Oh. If we move things a little bit, it is on one hand this multiplication, on the other hand it is 64 multiplied by 720, and we can put the C in the denominator, changing the sign of its power. Now we can ask Wolfram if we can write this as nicer. Factor fraction is 64 multiplied by 720. It's 21 above 1024. Okay. 10 times 2.
Yeah. I don't know why they're exactly close, but okay.
So we need to estimate this thing, meaning we need to find an upper bound and again, a good one. Maybe not the tightest, but a good one. So we know that C is some point between 1 and 2. Generally, we get here when we know, again, we know N and we know X and we know A, we get an expression of C, and we need to find a good upper bound, which is preferably the maximum of the expression. One can, generally speaking, in the general case, find derivative is equal 0, and so on in order to find the maximum. Here, and in most cases, in most such questions, we achieve an expression that it is easier to, it's pretty easy to understand what is its upper bound, its supermum even. We know that when the denominator is big, the fraction is small. That's what the Neanderthal used to say. Big denominator, small fraction. Blah, 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 blah. Now, for C equals 1, we get the supremum of our expression, which is a good upper bound and a good estimation of the error is smaller than 21 above 1024. So, in conclusion, when the series is alternating, we use the element the arrow starts with as the upper bound or as the element we use to find the minimal n, as we showed. When it is not alternating, you can observe that the series is almost alternating, but we have two first elements that are the same. We're having the same sign, and then we start the alternation. So we use the alternative in the non-alternating case. We use the general form of Lagrange, which leads us to some expression of C, and we know where C is. We don't know exactly who it is, but we know where it is. So we are looking at the supremum, and it is our desired upper bound, desired estimation of the error. Yet again, we can check if it checks out, going back together to the Wolfram, and you in the test you do have your calculator with you. On one hand, the real error is the square root of 2 minus our number here. That was our approximation. So let's fresh. The real error is the square root of 2 minus our approximation. It's minus 0.1156. This is the remainder. The error is the absolute value of the remainder. And our approximation of the error is 21 above 124, 0.02, which is indeed greater than the real error, which was something like 1.0, going to 0.01 or something like that. So yet again, it actually works. Okay. Should check yourself whenever you solve such an exercise that you didn't miss a crucial element. Your error is actually too big than your estimation. Okay. Any questions about our Wolfram check or the example using Lagrange to estimate an error?
But why did you put C1? Because you're maximizing the error?
Yes, I want to find an upper bound, and I want to be good. I'm not crossing a tight one, but a good one. So the supremum is actually tight. Yeah. Now the problem is we don't know what C is. So the actual error, I don't know what the exact C that gives it, but as we've already seen in Wolfram, it is smaller than our bound. It's not the bound itself. It's not tight. Actually tight. Any other questions? So for my last point about Taylor series and calculus of one variable at all. In the last 3 weeks of the semester, we will discuss multivariable calculus. There's a question we've already asked on Sunday. How do we, to begin with, how do we know that a function actually equals some power series? Now, the geometric series, we know it equals 1 above 1 minus x using some infi1 mumbo jumbo. But e to the power of x and sinus x and all that was given to us from them, the cosinus x and our estimation today, we assumed that they are equal each one some power series, but we don't know, but we didn't explain how to show it. And of course, we didn't show it. Now, using the Lagrange form of the remainder, we can explain when function e equals a power series, or at least give some sufficient condition. So that's our headline. How do we know that function? No, without headline. How do we know that the function f equals power series sum an x to say the power of n? So first of all, we already mentioned f has to be infinitely differentiable. Because the power series is infinitely differentiable. You can differentiate it as many times as you want. So if f equals power series, it has to be infinitely differentiable as well. But moreover, now we know that if we want f to be copy all of its line and paste it here. If f equals, if we want f to equal power series, it has to be the Taylor one, as we already proved on Sunday, and Taylor is the Taylor polynomial and the remainder. And the remainder, we know that by Lagrange, it is this nice little fellow. This is what f actually equals. Now, by definition of infinite sums from first infi, the limit when big N tends to infinity of Pn is the series. Why? What are you doing? I know what to do. You can't see it, but I can see it in the work. We know that the limit of Pn is the Taylor series, is the infinite sum. Yeah, the limit of the partial of the finite sum is the infinite sum. Nothing new. But if we want f to be equal to the infinite sum, and we know that the Pnx goes to the infinite sum when n goes to infinity, the remainder should go to 0. So in the end, when we put the limit when n goes to infinity, we are left with only the series. So in order to get what we want, get f equals the sum, the infinite sum, we need that as I've already mentioned some lectures before, Rn goes to infinity, and in our case, we can say that it is enough to this limit, somewhat it's writing different words, that this one goes to 0 when n goes to infinity is enough. If the function satisfies that, is enough for the function f to be equal to a power series around A. And we know that power series will be the Taylor series. If the function equals the power series, we've already proved that it must be the Taylor one in lecture number 18. But here, I want to answer this very question. How can we know that the function equals the power series? So we want the remainder to go to 0, which means this should go to 0. Now you tell me. Don't. This nice little fraction can be written as the multiplication of x minus a above x minus a to the power of n plus 1 above n plus 1 factorial blah, blah, with fn plus 1 at c. Why is it good to look at it that way? Now you use your computer science knowledge. Who is stronger? The exponential in the numerator or the factorial in the denominator? Who wins?
Exponential.
Factorial is stronger, greater, better than the exponential. The fraction in light blue goes to 0, no matter what x or a are, because factorial is asymptotically greater than exponential expression. Okay. But it's not all. This one goes to 0, right? But it is multiplied by the derivatives. So in order for the whole limit to go to 0, what we can require from the derivatives what is enough. Yes, it's exponential versus factorial. Decreasing, no, it will work, but we can require something weaker.
Not dependent on n, but
More of that. If this goes to zero, a multiplication of two things, one goes to zero. We want the multiplication to go to zero as well. The second thing should be bounded. Bounded multiplied by zero goes to zero. So it is enough. So if all derivatives of f are bounded, it is enough. It is not necessary. I mean, one can think of an example where the derivative is n. It's not bounded, it goes to infinity. But again, you multiply this weak-ass polynomial with the exponential, divided by the factorial wins. Yeah? So it is enough, it's not necessary. Now, on the other hand, we need the derivatives to be what is called uniformly bounded. I mean, one can say, you know what? The first derivative is bounded by 1, and the second by 2, and the third by 6, and the fourth by 24. So every derivative is bounded, but it's actually bounded by n factorial, which is not good. Multiply by n factorial, it will not go to 0, right? So are uniformly bounded. This is the right notion. What is uniformly bounded? There is a real number m greater than 0 such that m is greater than the derivative for every n and every x in our domain. So this is we can write it. We can conclude it. Let's call it Taylor theorem. Okay, that's about Taylor. Taylor theorem. Let f be an infinitely differentiable function at the point A such that there is a real number, blah, blah, blah. And for every x in, as we already know, we're talking about every closed interval. So A is the center of the interval. So let's write something like A minus R, A plus R. Already familiar with the notion when we talked about power series before, then we mentioned the Taylor one. Then F equals its Taylor series. Any questions about that? We have two last questions. We're not going to answer them as I wanted to. We're not running out of time, but it's okay. We will manage. First of all, our specific functions, e to the power of x and sinus x. Why do they satisfy this condition? Why do they actually, each one of them equals its Taylor series? And sinus, all its derivatives are sinus and cosinus, and they are bounded. It's easily to see. What about e? It's a bit tricky. I mean, derivatives of e to the power of x are e to the power of x. And in all of R, e to the power of x is not bounded. But that's not what we're saying. We're looking at every closed interval in R. And in every closed interval, a minus r to a plus r, the derivative of e minus x, which are e minus a, e to the power of x, excuse me, e to the power of x, are bounded by e to the power of a plus r, e at the right end of the segment. So it's not bounded on all r. You don't need it to be bounded on r. We need to be bounded in every closed segment. In every closed segment, it is bounded. So this is first question. Why do our functions sinus x and e to the power of x satisfy these conditions? They do. Notice that we don't need the derivatives to be bounded in all r. We need to be bounded in every closed segment. In a closed segment, they're bounded by something else. Fine. The second and last question today here is a counterexample for a function that is infinitely differentiable, but hey, its derivatives are not bounded, and they are not bounded badly enough, so this limit is not zero. We mentioned, let's say that the derivatives are n. Multiplying by n won't change the tendency of the expression to zero, but multiplying something worse, like n factorial, will change it. So for an example, and then just write down because we're running out of time, an example for a function that is infinitely differentiable, but does not equal its Taylor series. One should be a bit creative. Look at the piecewise function. E to the power of minus 1 above x squared, where x is not 0, and 0 at the point 0 itself. We are not going to do it. I don't have the time, but one can show, because the function is piecewise function, you should do it by the definition of the derivatives, but one can show that at the point itself, all the derivatives are 0, so the Taylor series, all of its elements are 0. Taylor series is just 0, which is different from function, of course. More precisely, there is no such a segment, let it be a big or small one, in which the function equals its Taylor series. It's only at the point itself. And why is that? If you calculate derivatives, not just at 0, but for every x, you can see that around 0, they are not bounded. They are very big. But we're not going to do it today or any other day. Okay. Any questions about what we did today?
And it was understood, yeah, just I just find it interesting that the remainder goes to zero, and it doesn't matter at what rate, it's fine if the function is bounded for it to be a real function, like a function equals to a sum. We'll do it later, but like, yeah, it doesn't matter at which rate it goes, it's fine. Like x can be whatever you want,
And a can be whatever I want.
yeah.
Yeah, it's still factorial comparing to an exponential. As I mentioned before, the piano way of looking at the remainder is talking about its asymptotic features. One can show that it's O of small o, not big O, small o of x minus a to the power of n, Rn goes faster than that, to 0. Any other questions? Okay. Sammy, you got any question?
Nope.
Okay, so you do you. Stay safe. And then we meet again on Sunday. Bye-bye.